Hello, this is John Melendez, and this is a lecture on the central limit theorem. Let's go ahead and begin. First of all, you need to know what a sampling distribution is. Basically, a sampling distribution is when you take samples of a certain population. You take sample after sample after sample after sample after sample, and you make a probability distribution with that sample. Now, let's look at this. Let's look at this thing that we have here. I've showed you in class before. This is a population right here. Let's make it normal. Okay, so we have a normal distribution right there. Now, the mean of this population is 25, and the standard deviation of this population is 8.2239. Okay, so basically, the first theorem that we have here says that the sampling distribution of the mean is the distribution of sample means, with all samples having the sample size n taken from the same population. The sampling distribution of the means is typically represented as a probability distribution in the form of a table, probability histogram, or formula. What that means is basically that you have samples after samples after samples after samples after samples, and you take the sample means of those samples and you make a distribution, a probability distribution. Okay, so let's look at this. Okay, let's look at what happens here. Now, let's look at some things right here. Let's say that we're coming for a population sample, right? A population mean, a population, normal population. We're going to take samples. Now I'm going to take a sample of 2, and I'm going to take only one sample. I took one sample, and there it is. 2 things in that sample. There it is, one sample. And this is the distribution of the sample means. In other words, you're taking all these samples, and you're getting the information from them. Notice that the sample, the mean of the sample is 13, while the mean of the population is 25. And the mean of the sample, the standard deviation of the sample is 1.4, while the population standard deviation is 8.22. Notice, because we only have one here, it's the same thing, and we don't have a standard deviation. You can't with just one. Now, let's say that we want to take several other samples. We want to take 100 more samples. So what's going to happen here is we're going to take sample, 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 sample. We're going to take 100 samples. This will be the distribution of the 101 samples that we've taken. Okay, so let's try and see what happens. Okay, notice that we have here, this is the last sample, the 101st sample. This is going to be the distribution of those samples. It doesn't look quite the same as this one doesn't. So what we're going to do is take more samples. We're going to take 10,000 samples. So if we take 10,000 samples, notice what happens here. This is the last sample. This is the 10,101 sample. This is the distribution of all those samples. And notice what happens here. Now the mean of the population and the mean of these samples are the same. If we increase our sample size, we can go ahead and do more. So I'm taking about, let's say that we have 150,000 samples, about. Notice the distribution of the population and the distribution of the sample means. They're the same. They're coming from a normal distribution, so the distribution of the sample means is the same. They are equal. Now, one of the things you might want to look at here is this. You can see that this one right here, that the mean for the population was 25. Now the mean for this one's going to be close to 25. We take more samples here, and more samples and samples. Go ahead and take more and more samples. And look at this. This is going to be very close to the population mean right there. Now the other thing you can see is this. Notice that this is your standard deviation of 8.2239. And this is 5.80. Now, if you take the population standard deviation, in other words, this one right here, of 8.2239, and you divide it by the square root of 2, because our sample size was 2, you're going to get something close to 5.8069. They're going to be close to each other. Now, that's basically what the theorem is saying right here. Okay? Given that the random variable x has a distribution which may or may not be normal, that's the central limit theorem. But now this one, what it's saying is that the mean of the population and the mean of the sample, the distribution of sample means are going to be equal. And the standard deviation for the sample means is going to be equal to the population standard deviation divided by the square root of your sample size. Now, let's look at this. Let's say that we have this right here. Now, in our little exploration right here, I'm sorry, that's not it. In our exploration, let's say that this distribution was not normal. Let's say it was any other one. Let's say it's a skewed distribution like that. Now, if we take, let's just make it 1,000. We take 1,000 samples, 2 of each. We get a distribution that does not look normal. Notice that the mean of this one is 15, and this one's close to 15 too, but still, they're not normal. Now let's keep on going. Now, notice this. The distribution here is skewed, and this distribution is skewed. Now let's change this to 30. Now this means that now we have 30 in the sample. Now, and we're going to take 10,000 samples right here. And we get what? Look at this curve right here. We get a normal distribution. So what that is saying here is this, that the central limit theorem tells you that if you have any distribution at all, as long as you have more than 30, then you can have a normal distribution. So for size n larger than 30, the distribution of the sample means can be approximately normal, no matter what, as long as you have 30 or greater in your sample size. Now, if your original population is normal, it doesn't matter what size sample you had, because you already know it's normal. Now, the things you need to know is this. This is the mean of the this is the mean of the distribution of sample means. Okay, and then this is the standard deviation for the sample means. This right here is called the standard deviation for the sample means. We shorten to the standard error, and that's going to be a test question. So that is a standard error right there. Now, the procedures when we come to the central limit theorem problems are going to be here. Number 1, write your parameters, all the information given to you, using symbols, and write your probability statement. Okay, once you do that, you find your standard error. Take the standard deviation divided by the square root of your sample size. Once you do that, use the formula z equals to the x bar, which is your sample mean, minus your population mean, divided by your standard error. We convert that into z-score. Then rewrite this probability statement that you had on step 1 into a z-score, z-terms. Then find your probabilities. Let's look at an example right here. We have assumed the population of weights of men is normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Find the probability that if an individual man is randomly selected, his weight is greater than 175. Okay, so let's look at this one first. This one, since it says an individual man, you're not applying the central limit theorem problems. All you're doing is the regular ways that you did it before. Okay, so let's go ahead and write our probability statement. His weight is greater than 175, so we want the probability that x is greater than 175. Okay, so now we're going to write down our mean and standard deviation, our sample size. Okay, so we're going to write our parameters. Our standard deviation is 29, the mean was 172, and that should be a mu, 172, and then the x is greater than 175. Okay, so now what we have is we convert x into a z-score by using this formula. So we take 175 minus 172 divided by 29, giving us 0.10. Rewrite your probabilities in terms of z. So z is now greater than 0.10. Okay, then after we do that, we're going to find a probability. We're going to find a probability by going to the tables. Okay, so we go to 0.10, we go 0.1, and then out to 10, and we look at where we have it right there. Okay, so now that's going to be the area to the left side. So we want the area to the right side. So we take and subtract 1 minus this blue area, and we get our answer. So the answer says 46.02%. And that's how we do that problem. Let's look at another problem right here. Now, this time we have a sample of 20. So, we do the same ideas. We write down our information, okay? So we write our information down, 29, 172, but now we have the sample size of 20. We go ahead and do our probability statement, okay? But before we do that, we convert this into the standard error. So we're going to convert it into a standard error by taking the standard deviation divided by the square root of the sample size. Once you do that, you get your standard error. After that, you put it into the standard score formula, which is 175, which is your sample mean, minus 172, which was your population mean, divided by the standard error of 6.4845. Giving you a 0.46. Now that we have 0.46, we go to the tables. We go out here to 0.4 and then out to 06, and we find this number. And now what they were trying to find here, if you remember, was they were finding the probability that 20 men randomly selected will have a mean weight greater than 175. So we want the area to the right, but we only have the area to the left. So we have the area to the left, but we want the area to the right. See, this 0.6772 is right here. So we subtract it from 1 and we get 0.3228. Now, let's look at another example right here. The time it takes to drive between city A and B is normally distributed, with a mean of 14 minutes and a standard deviation of 2.2 minutes. Let's look at two examples here. First, we're going to find the probability that a trip between the cities takes more than 15 minutes. And then the second thing is going to be finding the probability that the mean time of 9 trips between the cities is more than 15 minutes. Okay, so let's look at the first one. The first one, we have the probability that a trip between the city takes more than 15 minutes. That's just an individual score. We're not talking about sample means. So we just do it regularly, just like we did on the other ones. So we're going to write down our information, and we have it right here. We write out our probability statement, and then we convert the numbers into z-score. After we do that, then we go ahead and find the probability that goes with 0.45 on the right side. Okay, so we have 0.45. So basically we go to 0.405 and we find its number. Okay, so now that's the answer to that one right there. Now let's look at this right here. Oops, sorry. Now let's look at this one right here. Well, now apparently there was I messed on the other one, so let's just do this one now. Records indicate that a package shipped by a certain trucking company has a mean weight of 510 pounds and a standard deviation of 90 pounds. 100 packages are being shipped today. What is the probability that their mean weight will be more than 530 pounds, less than 500 pounds, between 495 and 515 pounds? Okay, let's look at the first one. What is probability that the mean weight will be more than 530 pounds? Okay, so we write down our information. We know that our mean is 510. We know that our standard error is going to be our standard deviation divided by the square root of the sample size, which is going to be 90 divided by the square root of 100, which gives you 9. Now we find that 530 as a z-score, which is 2.22. We find that probability in the tables, and then we find our answer. So we find that number in the tables, and we find our answer. And that's how you work that problem. Let's look at another one. What about this one? What is the probability that their mean weight will be between 495 and 515 pounds? Okay, our first step is to write down all of our information. And then after we do that, we go ahead and convert these two numbers into z-scores by using the formula. Once we convert them into the formula, into the z-scores, then we find this probability by using the tables. And we get our answer. So what should the probability be between them? Well, it's this. Okay, so now let's look at the next thing. The next thing is that we want to review the binomial probability distribution because we're going to do an approximation to the binomial. Okay, now this is sort of like a central limit theorem idea. Okay, now let's look at our principle right here again. Okay, let's look at this right here for a moment. Now we have a binomial here. Okay, so let's look at this one. Tossing coins are basically a binomial. Okay, it has to be, let's see here. Okay. Okay, so let's look at this. This is a binomial distribution. Now, if our P was very low, like 0.10, our Q is going to be 0.8, and we're going to roll it 100 times and see what happens to the distribution. Now, does that look normal to you? No, it doesn't. Now, let's look at this. Let's increase it to 0.5. Now, if P is 0.5, then Q is what? 0.5. Now look at this. N times 0.5 gives you what? 5, right? Which is greater than 5, right? Or it's equal to 5, I'm sorry. So look at the simulation here. It's very normal. Let's up this a little bit more to 50 and simulate. And more. Okay, do you see how it becomes more and more normal? So basically, what it's saying right here is that, now this is just the review for those, but basically, that when n times p is greater than 5 and n times q is greater than 5, then you have a normal distribution. You can assume the binomial distribution is the same as the normal distribution, and that your mean is going to be n times p, and your standard deviation is the square root of n times p times q. Okay, so now, procedures for using a normal distribution to approximate the binomial distribution. You need to verify that both n times p is greater than 5 and n times q is greater than 5. If not, you must use software or calculator or table or calculations using the binomial probability formula. Then after that, you find the values for the parameters, the mu and the sigma, by using the formulas here. See, here's the mu equals to n times p, and the sigma equals to the square root of n times p times q. After that, you identify the discrete whole number x that is relevant to the binomial probability problem. Focus on this value temporarily. You might want to draw it out, okay, so that you can see where it is, because what you have to do is get the whole bar. Remember, when we have binomials, we have the bar. And then after that, you're going to find that area in a normal distribution. Okay, so let's look at this example right here. Find the probability that at least 122 men among 213 passengers. Well, we have this right here. It's between 122 and so forth, right? 213. So, what we have to do is find the normal distribution that goes to greater than 122, but then we have to subtract 0.5 on the left side and then 0.5 on the right side. And that gives you the answer. This has been the presentation for